another session of the office hours. I'm your host, Will, and today we're going to be looking at NetworkLessons.com on their OSPF tutorial. So let's get started. OSPF is a popular link state routing protocol. Routers will exchange pieces of information called LSAs in order to build a complete topology database, which we call the LSDB. These lessons will teach you everything when we start with the basics and work our way through the most advanced OSPF topics. In this course, you'll learn basics of link state routing protocol and OSPF, how to enable authentication in OSPF, what the different OSPF LSA types are used for, how OSPF uses different network types, what the different OSPF stub areas are and how they work, how to filter OSPF prefixes, and many other topics. The requirement is there is none, but the basics of routing is recommended. All right, let's do the first page. All right, OSPF is a link state routing protocol, and it's one of the routing protocols you need to understand if you want to do Cisco CCNA, NP, and IE routing and switching exams. In this lesson, I'll explain the basics of OSPF so that you can learn how and why it works. I don't know about you, but I love my navigation system. The good thing about them is you can drive and there's no need to look at traffic signs. The bad thing is I'm absolutely lost when it's not working. I'm bad at reading maps, and if I have to find my way to some street, then he's doomed. Link state routing protocol are your navigation system. They have a complete map of the network. If you have a full map of your network, you can calculate the shortest path to all your different destinations out there. This is cool because if you know about all the different paths, it's impossible to get a loop since you know everything. The downside is that this is more CPU intensive than a distant vector routing protocol. It's just like your navigation system. If you calculate a route from New York to Los Angeles, it's going to take a bit longer than when you calculate a route from one street to another street in the same city. Let's take a look at your link state and see what it exactly means. That's the interface of a router. What is? Oh, okay, it's trying to explain what link and state is. That's the interface of a router. A state is a description of the interface and how it's connected to its neighbor routers. All right, looks like the pieces of the LSAs build up the LSDB. Link state routing protocols operate by sending link state advertisements to all other link state routers. All the routers need to have these link state advertisements, so they build their link state database or LSDB. Basically, all the link state advertisements are a piece of the puzzle which builds the LSDB. If you have a lot of OSPF routers, it may not be very efficient that each OSPF router floods its LSAs to all other OSPF routers. Let me show you an example. So it looks like we have a couple routers and they are all connected to the same switch, and this is all in area 0. But if we have a network of 8 OSPF routers connected on a switch, each of these routers is going to become an OSPF neighbor with all the other routers sending hello packets, flooding LSAs, and building the LSDB. This is a diagram of what will happen. So this looks like a full mesh. Traffic's going everywhere. Everyone's getting flooded. We will get a full mesh of OSPF neighbors. Each router will flood LSAs to other routers. So we will have a lot of OSPF traffic. Is there a way to make this a bit more efficient, such that we only have one of the routers flooding out those LSAs? What if all our OSPF routers would just send stuff to a single OSPF router, who will then forward it to all other OSPF routers? All our OSPF routers will know about all the routing information out there, but we will have far less OSPF traffic. OSPF uses something called DR, designated router. All our OSPF routers will only form a full neighbor adjacency with the DR and not with all other routes, or not with all other routers. All right, it looks like we have one DR and one BR. Since bad stuff can happen to the network, we have a backup for the DR. If it crashes, the BDR will take over. All our OSPF routers will only form full neighborhood adjacencies with their DR and BR and not with other routers. This sounds efficient, right? We only use a DR BDR on a multi-access network. An example of a multi-access network is using a switch. There's no need to do this on a point-to-point link. There is only one other router on the other side, so there's no reason to select a DR BDR. Link state databases are a full picture of the network. In network terms, we call this a topology. You can compare the LSDB to having a full map of your country. Once every router has a complete map, you can start calculating the shortest path to all the different destinations by using the OSPF algorithm. The best information goes into the routing table. Calculating the shortest path is like using your navigation system. It will look up the map and look at all the different ways of getting to the destination and only show you the best getting out there. There is only one link state routing protocol we are going to discuss, which is OSPF. There's another link state routing protocol called ISIS. Enough of the link state routing protocol introduction. Let's take a look at OSPF and see how it operates. OSPF works with concepts called areas, and OSPF works with concepts of areas, and by default you will always have a single area. Normally this is area 0, or also called the backbone area. You have multiple areas, however, as in this picture above, we have areas 1, 2, and 3. All these areas must connect to the backbone area. If you want to go from area 1 to area 2, you must go through the backbone area to get there. It's possible for you to go to area 1 directly to area 2, you always have to pass the backbone area. Same thing if you want to go from area 3 to area 2. So why do we work with areas? Remember, good. Oh, sweet, I got a new follower. Thanks for the follow, Commander Root. So why do we work with areas? Remember that I explained about the navigation system. If you tell your navigation system to calculate from New York to Los Angeles, it will take much longer than calculating a route from one street to another street in the same area. This calculating is called the SPF algorithm, and the same thing applies to OSPF. Our routers only have a full picture of the network topology within the area. The smaller your map, the faster the SPF algorithm works. This algorithm was developed in the 70s, while OSPF was created in the 80s. In the picture, you'll see on the top right something called Other Routing Domains. This could be another network running another routing protocol, perhaps RIP, and it's possible to import and export routes from RIP into OSPF or the other way around. This is called redistribution. Routers in the backbone area, area 0, are called backbone routers. Routers between two areas, like the one between area 0 and 1, are called area border routers. Routers that run OSPF and are connected to another network that runs another routing protocol, such as RIP, are called ASBRs, or Autonomous System Border Routers. OSPF works differently than RIP and EIGRP. First of all, it's a link state compared to a distant vector, but it also doesn't just send link state advertisements around. Routers have to become neighbors first. Once we have become neighbors, we're going to exchange link state advertisements. Once you configure OSPF, your router will start sending hello packets If you also receive hello packets from other routers, you will become neighbors. A hello packet includes the router ID, hello at dead intervals, neighbors, area ID, router priority, the IP address of the DR and BDR, authentication password, and stub area flag. There's one catch, however. There are a couple fields in the hello packet, and many of them have to match, otherwise you won't become neighbors. Let's walk through the items in the hello packet and see what they are about. So we have router ID. Each OSPF router needs to have a unique ID, which is the highest IP on any active interface. More about this later. Hello at dead intervals. Every X amount of seconds, we are going to send a hello packet. If we don't hear any hello packets from our network for a certain amount of time, then this router is considered, or then the connected router is considered dead, and we are no longer neighbors. These values have to match on both sides in order to become neighbors. Neighbors. All other routers who are your neighbors are specified in the hello packet. Area ID, this is what area you're in. This value has to match on both sides in order to become neighbors. Routing priorities. The value is used to determine who will become designated or backup designated routers. DR, BDR, IP addresses designated, and PR, BDR routers. Auth password can be either in clear text or MD5. Stub area flag. Besides area numbers, OSPF has different area types. Both routers have to agree on the area type in order to become neighbors. Unadvertised loopback address. Wait, what? Each OSP router needs to have a unique router ID, which is based on the highest IP address on any active interface. There is a catch, however. On any Cisco router, you can create a loopback interface or a virtual interface, and you can configure an IP address on this. And when you try to ping it, you will always get a response. If you have a loopback interface on your OSPF router, then this IP address will be used on the router ID. Be used as the router ID, even when it's not the highest active IP address. Why does OSPF do this? Well, it makes sense. Your loopback interface will never go down unless the router crashes. Has the IP address. Using a loopback interface, you can do two things. Advertise the IP address on the loopback interface in OSPF. Don't advertise the IP address on the loopback interface in OSPF. What's the difference? If you advertise it, other routers would be able to reach and ping the IP address on this loopback interface, or you can use it to telnet into the router. If you don't, then you will say it's not as easy as that. Everything is, well, we have configured OSPF. We have become neighbors with a bunch of routers, and they have exchanged links to advertisements. Our routers have built their LSDB, and they have a full topology picture of the network. Next step is to run the SPF algorithm and see what the shortest path to our destination is. Remember metrics? The metric is what the routing protocol uses in order to determine the best path. The OSPF uses a metric called cost, which is based on the bandwidth of an interface. It works like this. Cost is the reference bandwidth divided by the interface bandwidth. Actually, you should write that down. Yes. you have a 100 megabit interface, what will the cost be? So 100 megabits, which, wait, where's the, oh, okay. The reference bandwidth is default. On Cisco routers, the reference bandwidth is defaulted to 100 megabits. So 100 divided by 100 is 1. If you have a 10 megabit, then the cost is 10. The lower the cost, the better the path. Alright, cool. Look at the picture above. We are sitting in the router. Look at the picture above. We are sitting in the router on the left and running the SPF algorithm looking for the shortest path to our destination. Which one are we going to use? Using the router on top, we would have a cost of 10 plus 8. So that's that and that, which is 18. The path in the middle is 5 plus 5. The router on the bottom, we would have a cost of 20 plus 20. Path in the middle obviously has the lowest cost of that. This is the path we're going to use. Look at this picture. As you can see, the path through the router on top and the middle router have the same cost. 5 plus 5 equals 10. What are we going to do here? The path is equal. The answer is load balancing. We're going to use both paths, and OSPF will load balance among them 50-50. Some things worth knowing about OSPF load balancing. Path must have equal costs. 4 equal cost paths will be placed in the routing table, maximum of 32 paths. To make paths equal costs, change the cost of the link. If a path is not equal, we can make it so by manually changing the costs or the bandwidth of the interface. Alright, one last thing I'd like to tell you about OSPF authentication. OSPF can do MD5 authentication. OSPF can do clear text authentication. You can enable authentication for the entire area or a single interface. That's all I wanted to explain to you about how OSPF works. I hope this has been useful to you and that you now understand how OSPF works. In another lesson, I will demonstrate how to configure it. If you enjoyed it, please leave a comment.